Ladies and gentlemen, welcome to the second part of Recitation 8. I'll call this Recitation 8.1. Well, just like I said in the last recitation, we will be talking about, we'll solve some problems involving matrices of order 3. And, the problems that I will solve are on that worksheet, number 3. All right, let's get started. Before that, I would like to address one previous problem from the last time. And that problem was the following. As you can see here, I gave you a hint on how to solve it. So using this identity. So let me just quickly say a few things. Well, we will look at this if we multiply a plus ib times a minus ib, right? This would be nothing else than just a squared minus iab plus iba plus b squared. And also, the other way around, if we multiply a minus I times b times a plus ib, this will be a squared plus iab minus iba plus b squared. In any case, we will have that this is a squared plus b squared plus I times ab minus ba, minus. And this guy will be nothing else than just a squared plus b squared minus plus I times AB minus BA. Okay, right? So we have this here. All right, that's beautiful. Now, we would like to apply the above identity. So applying star, so the above identity star for x equals a squared plus b squared and y to be I times ab minus ba, we have. So keep in mind that, okay, let's, and we should add these two equalities, add them up. So we will have that 2 times the determinant of these two expressions here will be the same. This guy, the determinant of this guy is the same as the determinant of this guy. So this will be 2 times the determinant. In fact, let's write it in this way so that you can see, because this will be a complex number times its conjugate. So this will be the determinant to a plus IB squared. And this would be nothing else than just the determinant of 2 times, the determinant of all right, let me write it like this so that you can see it. So this would be the determinant of a squared plus b squared minus I times AB minus BA plus the determinant of a squared plus b squared plus I times AB minus BA. Okay, now we will use this identity. So using star here, we will get that this last thing, it will be equal to 2 times the determinant of a squared plus b squared plus the determinant of I times AB minus BA. Okay, but this guy here is non-negative. If you look at this guy, this will be non-negative. So it will follow that. And this guy here, if we go a little bit further, will be 2 times the determinant of a squared plus b squared. And if we take I squared out plus I squared determinant of AB minus BA. And since this guy is -1, the conclusion follows. So this guy will be non-negative, so this implies, so the conclusion follows immediately. Anyway, that was a very tricky problem, I would say. Very tricky. But now let me point out a remark. So the question here, let's say problem 10. Let me put this as a problem. Well, does the inequality still hold true? Does does problem 9 still hold true if well, for 3x3 matrices, let me put it this way. For 3x3 matrices. Because the natural question is if we can extend the above inequality, so the above problem, if the size of the two matrices are not just 2, is not just 2, if it's 3. Unfortunately, the answer is no. And I will give you a counter example. So it's a plain no. And the counter example is the following. Let's cook up two 3x3 matrices such that this inequality is not true. So let me point out, I'm going to consider the following matrix. So this will be 0, 2, 0. And I'll have 0, 0, 1, and 0, 0, 1. So this is my first matrix A. So it's a 3x3. And B, I'm going to consider the following matrix, which will be similar in nature with this one. So 0, 0, 0. I'm going to put here 1, 0, 0. I'm trying to have as many zeros as possible. So maybe here I put 0, 1, 0. Well, I'll leave it to you as an exercise why this holds true. So you need to square both matrices. You need to add them up. You need to see the commutator, right? The additive commutator between them. And you will see that once you take the determinant of both quantities of a squared plus b squared and ab minus ba, you will see that the inequality is not true. Anyway, I'll leave this to you since I want to veer towards matrices of order 3. But I wanted to point out this because this is a very useful thing to see. All right, now let me do another problem, problem 11. So starting from this point on, I'm just going to solve problems involving 3x3 matrices. And the first problem that I have in mind, I don't know, it's classical, whatever, but it's a very nice problem. So let me consider a 3x3 matrix with complex entries such that trace of A is the same with trace of A squared, and it's 0. We have seen this condition before, so that this will imply something, but anyway, we'll see what it will imply. Show that if the determinant of A is strictly less than 1 in absolute value, then the matrix A to the power n plus the identity, so this matrix, is invertible for all n greater or equal than 1. Okay, so let's look at this problem. Well, once you look at it, something just immediately pops up in front of your eyes, which is that condition. So maybe this can tell you something about the eigenvalues, or maybe even if you don't even have to go that far, honestly. But this can tell you something about how the matrix would look like. So the main ingredients here, if you look at it, so let me remind you, so recall the Cayley-Hamilton equality for 3x3 matrices, right? Recall that a cubed minus trace of a times a squared plus trace of the adjugate of a, we have talked about this, times a minus the determinant of a times the identity. This will be the zero matrix. Now, we would like to obtain some information about these two guys, this and this. We already know what happens to the trace of A. This is 0. We know, but maybe I can say something about the trace of the adjugate. And now, let me remind you something, that the trace of also, we know that, well, I said this numerous times, basically in the lecture, in 8.1 lecture, I think. I said that the trace of the adjugate can be expressed in terms of the trace of A and trace of A squared. So we know that trace of the adjugate, let me write it again here, of A was nothing else. It was, I think, 1/2 times the trace of A squared minus the trace of A squared, right? That's, but now we know that this guy is 0, this guy is 0, so therefore this guy is 0. So now I can safely say that the trace of the adjugate is 0. Okay, that's nice. Now, from Cayley-Hamilton, this implies that A cubed is the determinant of A times the identity. Well, let's denote this by alpha times the identity, where alpha is the determinant, right? So this guy is alpha, where the absolute value of alpha is less than 1. So we have this equality. But now we would like to, let's see what we want to prove. So keep in mind that we would like to prove that this matrix A to the power n plus the identity is invertible for all n. Well, let's assume that by a contradiction that, so assume by contradiction that the matrix A is non-invertible. So assume by contradiction that the determinant of A to the power m plus the identity is 0 for some n greater than 1. All right, so we have this. And now we would like to obtain some way, we like to obtain a contradiction. All right. And now, let me look at the above relation. So let me look at this guy here, because this will be important. So I want to look at this guy. So I want to look at a cubed is alpha times the identity. Well, this implies if we raise to the power n, so from it follows that a to the power 3n is alpha to the n times the identity. So now what we're going to do is the following. So now because the determinant of a to the n plus the identity is 0, right? So since the determinant of a to the power n plus the identity is 0, it follows that the determinant of a to the power 3n plus the identity is also 0. I hope it's obvious why, right? Because we can decompose this guy here, right? So a to the power 3n plus the identity is, you can write a to the n everything cubed plus the identity, and you can decompose this, right? Anyway, I'll leave it to you as an exercise to figure this one out. Well, basically I just said it, but okay, so we have this, but we know that a to the power 3n, so this implies that so we know that a to the 3n is, so this implies that the determinant of alpha to the n times the identity plus the identity is 0, which is equivalent with, we can say that the determinant of, okay, let me do the computation so you can factor, so it's alpha to the power n plus 1 times the identity. So this guy will be, so this is a constant, it's a 3 by 3, so it's alpha to the n plus 1 cubed times the determinant of the identity, which is nothing else than just alpha to the n plus 1 everything cubed. This will be 0. Well, I'm sorry guys, as far as I'm concerned, this can never be 0, which is, this is a contradiction. So this is false because the absolute value of alpha is less than 1. So we're done. So where did the contradiction come from? Well, if you look, it came from this guy here, so by our assumption. So therefore, the matrix a to the power n plus the identity is invertible for all n greater or equal than 1, and we're done. All right, I think that was problem number 10 from the list. Now let me do another one, which is somewhat similar. Problem 12, what? Okay, problem 12, which is also problem 12 on the list. So problem 12, it's a very nice problem. And I think something similar was given at some point at the Putnam exam, much simpler than this, but this problem says the following. So consider matrices A, B, in M3 of C with, well, the first matrix will be skew symmetric, right? Let's write it here. And the second one is symmetric. Okay, so the first one is skew symmetric, the other one is symmetric. Prove that if the polynomial f of x equals the determinant of a plus xb, right, has a multiple root, then the determinant of a plus b is equal to the determinant of b. All right, so that's the, I think this was some kind of a Romanian National Math Olympiad 2010, I think. Anyway, it's a very nice problem. So let's look at it. As you can see, we have some information about this polynomial. So it has a multiple root. Okay. Again, we can actually write this polynomial more or less explicitly. First of all, we have that this guy, f of x, which is the determinant of a plus x times b. Well, this can be written as, let's say, the determinant of b times x cubed plus alpha times x squared plus beta times x plus the determinant of a. So I can write it in this way. As you can see, the coefficients are here, this and this. All right. Now let's and the degree with the degree of f is less or equal than 3. Okay. All right. Now we would like to obtain some information about the coefficients or something, maybe about the determinant. But we can do something. We can transpose this. Also, we can we know that the determinant of a matrix is the determinant of the transpose. So also we have that. How should I say? F of x is the determinant of a plus xb, everything transpose. So the determinant of this matrix transpose, which will be nothing else than the determinant of A transpose plus xb transpose, which is nothing else than just by applying the properties of the transpose of a matrix. This would be A transpose. And now this will be plus x times b transpose. And now let's use the information we have. So we know that the first matrix is skew symmetric. Look here. And this b is symmetric. So let's use this information. So skew symmetric, so this is the determinant of negative a plus xb, right? Or if you want, if you take the negative in front of it, so it will be negative 1 cubed, which will be negative, the determinant of a minus xb, right? Which would be nothing else than just negative f of negative x, right? So f is an odd function, so f is odd. That's beautiful. Well, if f is odd, then clearly f of 0, right, which will be the determinant of a, right, is 0. So this implies that f of 0 is 0. So the f of 0 is the determinant of a is 0. All right, so we have this information, again, very important information. And now our polynomial, and also so this implies that f of x, which is the determinant of a plus xb, is nothing else. So the coefficient, the last coefficient is gone. It will be the determinant of b times x cubed plus alpha x squared plus beta x. But maybe we can get rid of something, because since f is odd, maybe we can rewrite this even better. So this will imply even more. It will imply that this coefficient will just vanish, this guy here. So if you plug in, so since f of x is a negative f of minus x, right? If you take here x to be negative x, it follows that in fact alpha is 0. So f of x is nothing else than just the determinant of b times x cubed plus beta times x. So we have this. So this is how we can write our function. So from here we have to play around a bit. But there is one condition that we haven't used so far. You see, we haven't used that this has a multiple root. We haven't used this, so maybe we should use it. Now we know that how it looks like, but we know that f has a multiple root. Right? So what does this mean? So this means that beta has to be 0, right? Because so beta is 0. So f of x is the determinant of b times x cubed. And I think at this point, well, so this is the determinant of a plus xb. So put x equals 1, and we get the conclusion, and we obtain exactly what we want. So the determinant of b is nothing else than just the determinant of a plus b, and we're done. Very nice problem indeed, right? So that was the trick, just to look at to show that this is odd, and then you can get information about this, about the polynomial. Well, since the degree 3, so it has at most 3 roots, right? And since it has a multiple root, then that coefficient here, beta, has to vanish. There is no way beta can be non-zero. Okay. All right, so now let me do another problem. Problem 13. Wait, what? Problem 12, problem 13. It's a very nice problem. This was given at this so-called international mathematics competition. It's a worldwide Putnam exam. So any university from around the globe can send a team to this competition. And it says the following. It's like a question. Does there exist a real 3 by 3 matrix A such that the trace of A is 0 and A squared plus A transpose is the identity? That is the question. So this is International Mathematics Competition 2011. Well, let's see. So probably you would think that the answer is no. So the answer is no. Is no. So let's look at it. You see, I have the transpose there. So maybe I could just take the transpose. Why not? So by taking the transpose, the equality A squared plus A transpose equals the identity we have. And let's be careful here. So we have that, so we know that the so we have that A is the same as the identity minus A squared transpose, right? Anyway, by just applying the usual operations with which is, so the transpose so this is the identity minus A transpose squared, right? But we know that A transpose here, keep using this is the identity minus, so A transpose is the identity minus A squared squared. So this would be equal to, if we do all these computations, so this would be, so okay, so it will be, so 2A squared minus A to the 4th. So finally we have this race. So we have that, we obtained that A to the 4th plus 2A squared minus 2A squared, sorry, minus A plus A, sorry, is 0. Okay, so we have this. All right, now maybe we can say something about the eigenvalues of this matrix that satisfies this kind of stuff. So the roots of the polynomial, so let's look at the roots of the polynomial. So the roots of the polynomial x to the 4th minus 2x squared plus x. Well, it's clearly you can factor an x. So we have one of them is 0. So our 0, 1, and the other one will be a surprise. It's negative 1 plus minus square root of 2 over 2. So now since the roots are this, it follows that. So the eigenvalues, so because by Cayley-Hamilton, we that will be 0. So the eigenvalues of A are, let's write them like this: lambda 1 is 0, lambda 2 is 1, and lambda 3, 4 are -1 plus minus square root of 5 over 2. So these are the eigenvalues. And now we like to see what happens to the eigenvalues of, you see, I want to see what happens to the eigenvalues of A squared. So the eigenvalues, or by the spectral theorem, that the eigenvalues of the of A squared will be the eigenvalues of A squared. All right, so we said that the eigenvalues of A squared will be the square root of this by the spectral theorem. So are, okay, I'm not, nu1, let's say 0, nu2 is 1, and let's say nu3, 4. So will be the square root of this. So this would be, it will be 1 plus minus square root of 2, square root of 5 over 2. Okay. So these are the eigenvalues. But now we know something. If we want to go back to, so we know that the trace of A is 0. But the trace of A, on the other hand, is the sum of the eigenvalues. So it's the sum of these nu k from k equals 1 to 4. And well, there is a combination. Maybe it will give you 0, but on the other hand, and also we look at the trace of A squared, which is nothing else than the trace of what is it? A squared. So it's it's the identity minus A transpose, and this would be nothing else than the trace of A squared is the same as trace of that. So this will be 3. But this will be also the sum of the square of the, oh, sorry, here is lambda k. I'm sorry about that. But here will be the sum of nu k, which will be 3. So this will be a contradiction. There is no way this could be this could work together. So contradiction. All right. So the problem ends here. There are no such matrices. Now I want to do 2 more problems, and probably I'm going to stop. So problem 14. This was it's a very nice problem, very instructive problem. In fact, I'll give you the main ideas, and I would like you to finish off this problem. And the problem states the following. Now let me consider A, B be 2 and 3 by 3 matrices with complex entries, such that the following conditions are true. So A, B, everything squared is A squared, B squared, and B, A squared is the same as B squared, A squared. Show that AB minus BA cubed is O3. This is a classical problem, I think. I remember seeing this a long time ago. Okay, so as you can look at it, as you can see, we have this bracket here. So again, the commutator, the additive commutator comes into play again. So denote the bracket AB as AB minus BA. So this is what we call the additive commutator. So from Cayley-Hamilton, if we look at it, we know that, so what do we know? We know that x, let's write it in this way, generically, x cubed minus trace of a times x squared plus the trace of the adjugate of this matrix x times x minus the determinant of x times the identity. This is the null matrix. So in our case, x is the bracket AB. Clearly, the trace of the bracket may be, in fact, let me write it in English. Clearly, the trace of the bracket AB is 0, right? It's the commutator. And we would like to use these two equalities here to show that the trace of the adjugate, so keep in mind that the trace of the adjugate depends on the trace of the trace of the bracket, everything squared, minus the trace of the bracket squared here. So in other words, if we show that, so this guy is already 0, so the only thing we need to show, maybe this guy is 0. So that's a question. Now let's see who this guy is, because we have to write it. So we show that the trace of the bracket squared is 0. But in fact, let me write it here above. So we have that the trace of the bracket squared is nothing else than the trace of, okay, so it's AB minus BA squared, which is, if we want to write this, and let's do the computations, this will be the trace of, in fact, let me write it in this way. AB squared minus AB BA minus BA AB plus BA squared. So we have to take care of this thing. But this is, let's write it. So this would be the trace of AB squared, right? Minus, okay, plus trace of BA squared minus trace of ABBA minus trace of BAAB and this would be equal to, and now let's look, let's use our relations. So this would be, so AB squared is A squared B squared, so this would be the trace of A squared B squared plus the trace of B squared A squared minus the trace of AB BA. Okay, at this point it becomes quite clear what's going on here. So this would be equal to, well, for example, if you wanna, this will be, okay, let me write it in this way. So you can group them. So this would be A, B, B, minus, let's say, let's group this one with this one. So this will be minus trace of AB, BA, plus trace of B, BAA, minus trace of B, AAB. And now, if you look at this guy here, if you move A at the end of this, so it will give you a trace of A, B, B, A. So these two guys, if you will give you 0, and the same thing will happen with these two guys. So the sum will be 0. All right, that's great. So we got rid of this guy as well. So let's look at them. So this guy, we got rid of them. This guy, we got rid of them. So now at this point, we know that bracket AB cubed is nothing else than just the determinant of bracket AB times the identity. So we know this at this point. Now, if we, by some miracle, prove that this guy is 0, then we're done. But remember, we have something. We did this problem. So remember that trace of x squared is equal to the determinant of 3 times the determinant of x for any matrix x with complex entries, 3 by 3 matrix with the trace of x equals 0. So now if we show that the trace of bracket AB cubed is 0, so if we show that the trace of AB cubed, bracket AB cubed is 0, we're done. Again, you will proceed in a very, very similar fashion. And I think I'm going to leave this to you as an exercise. So this guy is an exercise. So AB cubed, will you just cube everything by the cube formula, and you just group them together as you did for the square case, and that's it. So we obtain that AB minus BA, everything cubed, is the null matrix, and we're done. Okay, that was the problem. Well, it's a very nice problem, I would say. And now, last but not least, I would like to do one more problem, and then I think I'm going to stop. So this would be problem number 15. And this was a Putnam problem. This was a Putnam A4 from 2002. Anyway, you will see that the problem has it's like a game, but anyway, let's see. In Determinant, this is how we call this game. In Determinant tic-tac-toe, player 1 enters a 1 in an empty 3 by 3 matrix. Player 0 and enters and player 0 counters with 0 with A0 in a vacant position, right? And and the play continues in turn until the 3x3 matrix is completed completed with 5 ones, with 5 ones, and 4 zeros. Player 0 wins if the determinant is 0, and player 1 wins otherwise. That's a very nice problem. Assuming both players pursue optimal strategies, who will win and how? Okay. So let's look at the problem. Well, it looks a bit scary because it's a game, but in fact, if you read the text carefully, you will see that it's actually very easy because we have a 3x3 matrix here, right? So it's a determinant, and we know how to compute the determinant of a 3x3 matrix. We have formulas for that. But there is one thing, so the play will stop. So the play is completed with 5 ones and 4 zeros. That's a very, and also player 0 wins if the determinant is 0, and player 1 wins if the determinant is non-zero. So at this point, it's quite clear what we have to do. So we have a 3x3 matrix. Keep in mind that we have a 3x3 matrix, and we're asked about basically about the determinant. So by definition, we have that the determinant of this matrix with this entry, so let's write A11, A12, A13, A21, A22, A23, A31, A32, A33. So the determinant of this 3x3 matrix, and like I said, there is a formula, whatever the triangle rule or Cezar's rule, this will be A11, A22, A33 plus A13, A21, A32 plus the third one will be A12, A23, A31. Okay, we have this minus A12, A21, A33, A11, A23, A32, and the last one is A13, A22, A31. I hope I didn't do any mistakes. So that's basically the formula that you can compute the determinant. So that's what we have to use, and we should be careful here now. Okay. But anyway, it's just a triangle or Cezar's or whatever. Those of you who don't know this rule, I'll invite you to my videos on linear algebra. They're on YouTube. And I think on lecture number 3, I'm actually discussing matrices and determinants, or lectures 3 and 4. All right, now let's see. Let's point out the following remarks. So note that the terms. So if you look at these terms here, basically they're the product of 3 entries. So these terms are products of 3 rows right? And 3 columns. Of the, let's say, related matrix. And let's write it so A11, A22, A33, A32, A13. So this is A21, and this would be A23, A31, and A12. So this will be the related matrix. And now let's see. It's quite clear. So player 0. Player 0 will win if he prevents what should I say? It prevents a player 1 win in what should so player 0 will win if he prevents a player 1 win in ordinary tic-tac-toe when he translates, let's say, the selections of the related matrix to the related matrix right? And back again. So that's the strategy. So it is well known that also, let me mention that player 1 cannot force a win in ordinary tic-tac-toe. So let's point out also player 1 cannot force a win in ordinary tic-tac-toe. So this implies that, so thus player 0 can always prevent a win by player 1 in determinant tic-tac-toe. Right? Okay, so at this point it's clear that so however there is always a winner in determinant tic-tac-toe. And thus player 0 can always win. Can always win. That's basically the problem. Anyway, this was a very simple problem. The only crucial thing was just this formula. So, okay, I think I'm gonna stop here. I would like to thank you. And next week we will start. So we've done with the matrices of order 2 and 3, and well, we did quite a lot. But next week we will talk about matrices of order n. Maybe I will also like to talk about the minimal polynomial a bit. Yes, I think I'm going to do that. So how is this related to the characteristic polynomial? Also like to talk about the rank of a matrix, why the rank of a matrix is important, and you will see how. And also there are some facts about the rank of a matrix, some inequalities that are very, very useful. And maybe I'll talk about this as well. And the third week, I'll talk about some special techniques in matrices, such as diagonalization, maybe I will talk about Schur's theorem, or even about Jordan canonical form and stuff like that. Okay, I'll stop here. Thank you very much.